maybe not defeat it. So I put up our last lesson's video a couple days ago. If you have a power outage during the thing, don't worry about it. You can get the video, and I'll shortly go into what we're going to do today. As I was working on getting the stuff ready today, everything seemed to break all at once. So it took me a long time to get a functioning script, and as such, there is very little explanatory narrative between each part. So I'll try to make up for that with today's talk, but I'm going to be actually doing updates live while we talk. So you certainly can follow along on the web server, but an hour from now, what's on the web server and what you see on the screen will be two different things. So I will update that after our lesson's over. It doesn't take me long to update it, but it's something I actually got to think about doing, or I end up putting files in the wrong place and then I can't find them again, which was part of why I couldn't get stuff to work earlier today. So without any further hemming and hawing, I'm going to go ahead and share my screen. And I will simulate going back to, oh, there's Blackie the board. So I've called this lesson 8, Unsteady Open Channel Flow. And we're going to go through a homebrew scheme in a rectangular channel. And we're actually going to do a steady flow problem with our transient solver. If we get things working correctly, it should produce an equilibrium solution, which is, I can't even spell it today, equilibrium solution that should produce a result almost indistinguishable from the steady flow solver. And then we'll run a swim model, same situation. And we've actually already done this particular example before. When we were doing the steady flow case, we had the case where we had a downstream weir and critical depth of the top of the weir. We specified a downstream pool depth of 8 meters and upstream 11,000 some odd meters. We had a flow depth of 5 meters. And it's a 5 meter wide channel, 55 cubic meters per second. Some value for Manning's End, and slope of I think 1 in 1,000. So we've done it before, and under most circumstances that would seem pointless, but because it's a simple enough geometry that we can check our transient tool against a completely independent way of calculating the situation. It's a good way to test any new stuff that we do. Same thing for swim. If you're swimming in some new situation with bigger sharks than you're used to, it helps to set up an example problem with the sharks that you are used to swimming with, and be sure that you're driving it correctly. So that's for today, and then the link should take you here. Yours will probably actually render bigger, probably something like that you can read. And I'm going to be using this notebook right now. I won't click, I'll click on it, but unless you actually load it into the right software, it just does a very interesting, this is called gibberish pigeon. So it's English looking words surrounded by gibberish. Very interesting programming language. I'm going to be working on the Python notebook directly, and most of the pictures that you'll see are backlinked to these things. So if you want to, I'm not telling you to do it right now because it probably wouldn't be terribly productive. But when you're ready, you can download this notebook. You would right click, save target as, open it in your Jupyter Lab environment. That's your Anaconda thing. Then you should be able to get the rendering that I'm going to be doing live. If you want to get the graphics too, you'll have to download the various JPEGs. When I steal other people's notebooks, which I do quite a bit, although it's not called stealing anymore, it's called modern time internet. I usually don't worry about getting the graphics unless it breaks something else, and then I'll go back to the original source, and there's usually enough information buried in the file to work your way back to wherever they got the picture from and load it in and get it to work all pretty. So as an example, I have this pretty picture here. I'll show you how you actually, so that picture links like that. And so when you get to the source rendering version, you can find the name of the picture, and it looks like I need something called Tidal Bore 14 square bracket 8 JPEG, which is right down here. So if I had a desperate need for the image, that's how to get it. Oh, good, it didn't break. I think I'm working here. So I'm setting up the file directory to make sense, just in case I do something stupid. So what I want to discuss today was, suppose we were tasked with having to implement our own unsteady open channel flow solver. It's a short step from this to including constituent transport in the flow equations. So this is worth doing at least once in your lifetime. And then again, for money, use professional software. So we solve the equations by mapping the physical system and the partial differential equations. And I've read this to you before. And we're using a finite difference scheme called the Lax diffusion scheme. And it's called Lax because that's the name of the first author that made the various spatial and temporal averaging decisions and got it to function. And it's called diffusion because we've actually created difference equations that have an artificial viscosity, if you will, artificial diffusion term, which helps keep them stable. It comes at a price. There are more accurate ways to do these calculations than this, but there is no easier way that works. So there's no point in starting with a hard way, because you'll see shortly that the easy way is hard enough. It is useful in practical problems, and it helps us understand what goes on under the hood of something like swim or HEC-RAS. Recall from last time that we ultimately did a whole bunch of pseudo derivation to get essentially at these two. I guess I know that I'm in class right now. Hope y'all don't mind if I complain about Outlook. Next to having a cat in the house, it's got to be the most disruptive piece of software that was ever created. All right, so there, my rant is over with. We created these two update equations. This first one is a difference equation that gives us the ability to update depth values at any location I in our computation domain at a time level t plus delta t, so at a new time, based on the water levels at the current time to the left and to the right of where I'm at, geometry to the left and to the right of where I'm at, incoming velocity, that's I plus one, so that's velocity leaving minus velocity entering, so that's a continuity expression, and then a spatial average of velocity. So it's using current information to project to the next one. Call it a projected value of y. And once that's available to us, we also can compute projected values of velocity at the new time level. So these are called update equations. I'm sure there's a fancier term for it than that, but update is good enough. Everything on the right-hand side is known in both instances, and the general practice is we update depth, and we're supposed to use that new depth to update velocity, but that doesn't always happen. And then we update velocity, and then we declare time is now at the new time level and repeat. There are a couple of considerations we need to talk about, which I will get to as soon as I get a piece of paper I can draw on, and I will switch to the overhead camera in a second. Is that gonna work? Yeah, I can change my video stream. All this high-tech stuff, I actually am at times really competent at it, but I have to confess that it's been a long day for me. And I know that Jawad doesn't need to hear that because it's just the beginning of the day for him. But I imagine here in Lubbock it is significantly colder than where you are. And the way I can test that theory is the water where you're living right now liquid? Yeah, he smiled. Yeah, so he's got liquid water. So the rest of us, that's an interesting concept. Our water is currently solid and will be for another day and a half. But it'll all get over with, and then there'll be all sorts of political and business fallout because of it. And as engineers, we call that job security. So, okay. So we have these update equations. But we have two important, what did I just do with my pen? There it is. Let me switch to the different drawy thing. Okay, stop video. Nope. Switch to the overhead camera. That didn't work out so good. Let's try that again. Ah, I got to turn off the background. Rats. Should I put a cat filter on it? I am not a cat, Judge. I'm not going to get over that for a long time. That's just kind of funny.
It honestly was one of the funniest things in a while.
Yeah, I have a brother-in-law that's an attorney, and even he laughed. And he was saying, we, as attorneys and judges in the court, we do some incredibly stupid stuff, but that pretty much takes the cake. So it makes the rest of us look good. So here's our channel, and for the sake of discussion today, assume we have discharge moving from left to right, and it looks something like that. We're going to simulate it by breaking up this space into these segments. We had a name for those segments. Does anybody recall the name? Well, it shouldn't be much of a reach of your imagination to figure out what the name of those segments are.
It's a segment reach.
Yeah, very good. And each one has some length to it, delta x. And if we, two mice, use the one that doesn't have the tail. If we look at our depth equation, and let's suppose we're interested in what's going on in this cell. So we'll call that the I. There's the I minus 1 and I plus 1. So I'm normally numbering from left to right. That's a choice. That doesn't affect anything one way or another, but you have to make that choice up front. And as time progresses, it says that whatever the new depth it's going to be based on the depth to the left where it currently is and to the right. Similarly for velocity. But when we get to the new time level, we need to know the value of depth. And so I have time moving up. Forget the blue line that's confusing the heck out of you right now. At the new time level, we need to know what the depth and or velocity is at that location. So those are the boundary conditions. So there's going to be an upstream boundary condition of some importance. I'll just call it UPB, upstream boundary. And we have the same problem at the downstream end. We will need to determine values along the boundary, but we don't know what they are. But we do have a property called characteristics, which essentially takes our partial differential equation, restructures them as a total derivative, and that total derivative is creating a curve in the x time space, and it's possible to extrapolate boundary values for that. And I mention that because when we get down to the example problem, I'm simply going to show you what those boundaries are, and we'll talk about how I came about pulling them out of my datum later. I used to have a nice drawing that explained it, and I was looking, that's what I meant by losing files. I was looking for it all day today. And this is not the kind of thing I can do from memory either. So here is our problem statement. We're going to do a rectangular channel with a discharge over a weir, in our case at the right-hand side of the drawing that's in the little teeny box that's barely visible. Channel width is 5 meters, bottom slope 1 part in 1,000, Manning's N 0.02, discharge 55.4 meters cubed per second. And we're going to build a transient solver. And even though the problem itself is steady flow, we can use that. We can check with an independent tool, which was the Hamming's approach that we did a couple lessons ago. And we have to start somewhere. So I'm going to choose to start with a depth artificially large. Namely, not that that's the smartest decision, but more importantly, it's easy to script as you're developing a script from scratch. So if the depth's artificially large, so let's say in the drawing that I have here, let's say at equilibrium, the correct flow system should look like that blue line. So if we start with a depth artificially large, say the red line, say I say, well, that's my initial guess of the water surface elevation. And we have a fixed discharge here and fixed discharge there, and they're the same. So it's a steady flow situation. What does your intuition tell you that as we're doing computations that red line should do relative to the blue line? Go ahead, make a guess. You can't be wrong. I'll only slightly humiliate you if you're completely wrong.
Wait, were you drawing? Oh, I didn't see that you were drawing on your.
Yeah, up here where there's
Here,
motion.
hold on.
So we start with depth artificially large, and let's say equilibrium conditions are such that the depth should be at the blue line. Let's pretend that we really did start with it at the red line. What would the red line have to do at the upstream end?
Would it have to be contracted? Like the size of the reach would have to be smaller?
Okay, we'll keep the reach constant. I think you're along the right. You all know the answer. You're just having trouble articulating it. The red line should approach the blue line as time progresses. So imagine this is what the channel was like, and we somehow magically filled it up instantly using computer-generated imaging via Star Wars kind of stuff. So if we started a simulation with the red, after a little bit of time, we would expect the channel, the red line to start to drain out. Stuff has to get out until eventually the red line and the blue line would coincide. That's what's meant by the equilibrium solution. And so I choose, out of simplicity, to start with the water surface elevation prediction too big, so everything has to drain out. You could just as well start with it too small, but the problem with doing that is if you can start with it too small, why not start with it with 0? And if you put everything at 0, stuff just doesn't work. And then you'll have to go to the subway corporate job application site. So let's start with everything too big. And then the pretty picture here is intended to be motivational why you would even bother with a transient solver. So this line right there in your fluids lab, you would recognize that, oh, that's just a hydraulic jump, big deal. Well, the big deal is probably 30 seconds before the picture was taken, the hydraulic jump was here, and in 30 more seconds, it's going to be over here. So there is a wave that's propagating upstream. It's called a tidal bore, not to be confused with what I'm like at a dinner party, a different type of tidal bore. And so the velocity at any point in this system is changing both with space and time. So that is one of the common uses of a transient solver, is to be able to track the position of these bores as they move up and downstream. That one's not very tall, but there's some of them that have 22 feet, 9 meters difference in depth. It's like 27 feet tall, bigger than a ship. And so if your ship is in the wrong place when the tidal bore starts coming up a channel, you have a problem unless it's a submarine designed to be underwater. So that's one example of why we care about. Another one example would be if we're actually discharging materials into this channel, if you will. Say there's a wastewater treatment plant here, and we want to ensure that we're not, that we have sufficient mixing and dilution, that we don't violate any of our agreed upon permits and have to start getting the corporate checkbook out and writing a 1 with 5 zeros after it and handing it to the Environmental Protection Agency, because all they're going to do is turn around and hand it to a college professor, and then they'll flush it down the toilet. So basically, to keep the tax dollars in your pocket, we want to avoid permit issues. So that's the motivational picture. Now, this particular photograph is taken somewhere in the world. Can anybody hazard a guess by looking at it? So this part of the lesson is paying attention to photographs when people are trying to tell you a lie. So this photograph taken in Ecuador. So how do you know that's not Ecuador?
There's a Canadian flag.
That's a good giveaway. Excellent. The other one is the mansard roofs. Mansard roofs are a French architecture feature. So not only is it in Canada, you can actually probably guess the province.
Well, probably like Quebec or something.
Quebec, yeah. So I am descended from Quebecois. So I'm not sure. I didn't take this picture, so I'm not sure if I've been exactly there or not. But I do remember as a boy, when we go to the Northeast, in Canada and Prince Edward Island, that you would see these when the tide changed. These walls of water would come up the stream. You didn't want to be in the water fishing. Plus, it was plenty cold enough to discourage that in the first place. So the remainder of today, we're going to try to develop a script that's going to implement these concepts. I'm taking some big steps here, so don't be ashamed or discouraged if it looks like you haven't seen a lot of this before. I know that every one of you can read, and there is enough reading material on the server, you might have to take some time on your own and wade through it. So I ported this over from an old Fortran program that I had, and actually we can look at the Fortran program briefly, assuming I can find it in the readings, because it is out of this book. Oh, it's the missing chapter, isn't it? Damn it. I keep doing that. I don't think it's in chapter 10, but I'll try one more time. Inflow, Hydrograph, Predictor. I said last time I was going to go find the correct chapter, didn't I? That's my bad. Well, okay, anyway, I took the actual original program, and so this represents translating Fortran into Python, which just having just done it, I recommend that you avoid that like the plague. What was chapter 12? Undisplayable. But that was the main document that I was using. Nope, nope, nope. This one, computational hydraulics, has a pretty similar program of what we're doing here. But the important feature in Robertson and all is the adaptive time stepping. So we're going to see that, and I'll tell you what it is when we get to it. Okay. So we're using our cool online tool. It's supposed to be the latest, greatest thing. And if we were chemical engineers, it would ensure that we get $30,000 more per year payment, because they had a big study that they commissioned that proved that was true. So whether the Delta dollars has anything to do with any programming skills, I think is disingenuous. So we're going to build our hydraulic functions again. This is no different than the last time, except going from a rectangle to a trapezoidal channel is almost trivial, and yet a trapezoidal channel is a geometry that has some actual value, because we can approximate a lot of real world stuff with trapezoidal channels, especially if we get fancy by letting the side slopes be different on the left side and the right side. In this case, that's not the case. It's a trapezoidal channel as you're accustomed to. So a top width function, an area function, and a wetted perimeter function. So those are just slight variations of before. And we'll go ahead and we will create some problem constants. So to generalize this script, we won't get to that today, but to make it generalizable, we would be obligated that once we get it working the way we think it works, all that has to be handed off to some kind of input file or input interface so that we can change conditions as needed. But for this case, we'll start with gravity being set to 9.81, obviously SI units, obviously on the Earth. If we're doing Martian hydraulics, the acceleration of gravity is a little bit less than 6 meters per second squared, which kind of screws everything up, but it makes for good movies. We're going to break our thing into 10 computational reaches. Initial discharge is given the problem statement. Downstream depth is set at 8 meters, upstream is 5. Those are somewhat pulled out of my datum, but they're close enough to what will actually work under these conditions. Manning's N is 0.02. Bottom width is set at 5. Longitudinal slope constant for the entire simulation. So this does not yet allow the same flexibility that a professional model would, where the slopes can change as you're moving up and down stream. Side slope of the channel is just used to represent trapezoids versus rectangles. And we're taking a total length of 11,380, which is pulled right out of the example problem from a couple of classes ago. So that at first appearance would be, why that number? Why not 12,000? That's a fair question. We can keep track of simulation time unless we do some effort to use a time unit other than seconds. Because if we switch from seconds to something else, we're going to have to deal with switching that and that. So it's generally easier just to do everything in seconds and then convert it to a humanly fathomable time unit at the end. So I'm going to run it for 600 seconds, which is 10 minutes. And hopefully in a 10-minute simulation, we will be able to learn if our things are working like we want them to. A little bit of old-fashioned programming technique. We're going to have it print every time step, although that's a changeable value. So if you have to do 80,000 time steps for some kind of problem, you don't really want to print 80,000 outputs. So you want the ability to, well, I think I'll print every 10,000. Then it would only be 8 time steps printed, but it's still doing the intermediate ones. That same feature is in Swim. We don't know that we're doing that, but when we check, when we're in the timing interface in Swim, and we're selecting reporting times every 5 minutes, every 15 minutes, that's essentially what we're doing. The same thing here is we're telling it, as it's computing away, when do you want me to write output? And you don't want to write output every time. When I was learning how to do this a long time ago, it was even before water was invented, when we had output, it actually went to a line printer. And so we were very careful on output because you could end up killing an entire forest in a matter of minutes by putting the wrong number in. Nowadays, all you do is just kill a hard drive, which probably kills more forests in the long run. Anyway, that's beside the point. And then we're going to have the ability to count beyond our boundaries. For the time being, you're just going to have to take it on faith that this is a useful construct to be able to go at least one boundary position beyond our computation domain to handle the left and right boundaries. Now we're going to square Manning's N because it appears a lot. It's a pain in the neck to try to remember to type it correctly. And our flow area at the beginning of time. So that's going to be the area associated with the downstream depth in this case, our initial bottom width, and the longitudinal slope. So that's actually a function call. And it's okay because we already defined the function ahead of time. Boy, we're smart. If we don't do it, it gives us the pink block of errorness, and then you have to decipher the gibberish code that comes out. The next thing is we'll set an initial velocity. And we'll just make it the same everywhere because we don't know what the what the equilibrium velocities are. We'll just take the stated discharge, divide by the initial flow area. That'll give us a velocity, and we'll just assign that everywhere. So our next part is to now build space to keep track of everything. So the things we have to keep track of are depth, velocity, and then we're going to have that updated depth, the depth at time t plus delta t. So I call that y sub p, the projected depth, and the projected velocity. We're going to have the ability to calculate top width, which in this case will just be a constant everywhere. There is a need for a temporary variable for storing depth and a temporary vector for storing velocities. And this last part, we're going to convert this collection of zeros into, we probably actually could have just done this step up here, but then never mind. We're going to convert the initial depth and initial velocity to the downstream flow depth everywhere. So it's going to be too large except at the downstream most location. And we'll just put initial velocity everywhere. So this part of a script is similar to what we do in a professional program when we're drawing all the nodes and linking everything with little linky doodles. Internally, you're actually building an input file, and an input file is providing to the computation engine the number of things it's got to deal with and how the things are connected to one another. So we're doing the same thing that we would be doing in a swim or HEC-RAS. So let's see what else is there to comment. If you're new to this particular scripting language, this is a pretty cool structure. What that does is it's going to create a list of zero, and there's going to be n of them. So the listing syntax times nn creates nn elements of a vector y. They're all zeros. And then this is something called an implied constructor loop. The English word jargon is actually harder to understand than doing it. So what it's doing is it's creating y, it's populating our vector y, which already exists now. It has nn zeros in it, and we're replacing those nn zeros with values y sub d, and we're forcing those to be floats so that they have a decimal point in them. You don't always have to force floats, but we're doing some division and multiplication later on, and it's in our best interest that the computer thinks that they're all floating point values. And here we're doing the same thing for the velocity. Okay, the next block is pretty straightforward. We are computing the top width at the downstream end. We're computing something called the celerity, which is the gravity multiplied by area divided by top width. So that represents the speed of a shallow wave propagating in an open channel. And that's called the celerity. And the celerity plays an important role in how we're going to do time stepping. Because if we compute things and our time step is too big, we haven't provided enough time for the solution to advance. And so we'll be introducing, not only will we introduce errors in terms of accuracy, we'll be introducing phase errors in terms of stability, and it won't work so good. So if you recall, in either swim or HEC-RAS, which you all have probably used before in other classes, they have an adaptive time stepping in. So internally, they determine the celerity in each of the computation things, and they use the largest value of time stepping that they can. If you recall from swim, if you used it before, you have the ability to choose a routing time step. And I believe the default is 30 seconds, and you can choose anywhere from 1 second to, I guess, 300 seconds. And it will automatically cut that time step in half all the way down to less than 1 second, and then it will issue a warning message because it's running out of the ability to divide things. If you have a time step of 1 second, a celerity of 1 second represents water moving probably 30 or 35 feet a second, which is unheard of fast. So generally, if you haven't used that sort of time step, you've made a conceptualization error. And it's a nice way of saying human being, rethink your problem. So here we're going to use the celerity later on to calculate what time step to use for the numerical method that we're employing. The next term calculates the length of a reach. These distances here, I'm drawing on the picture now. Whatever that distance is, delta x, and it is the whole length of the computation domain divided by how many parts we've broken it into. So that's a no brain required kind of thinking. Next, we're going to need to know where we are in space later on for plotting. And our little comment statement to us tells us that spatial location of nodes, or I guess cross sections, that are used for plotting. And we're going to take the delta x that we've just computed, and we're going to multiply it by the position starting at 0 going up to nn in steps of 1. Next, we'll compute bottom channel elevations, which is, well, I started at 12. Oh, I had mental prior knowledge. Okay, so I have a bottom channel elevation, and we're flowing from left to right. So I've declared the left thing at elevation 12, and working our way to the right, we get almost down to 0. And so all we're doing is taking some reference position and subtracting off the slope times the x position associated with it. And then we're making an initial water surface elevation, which by definition is simply the bottom surface elevation plus the flow depth, which initially it will be too large. And actually we'll go ahead and plot that in a little bit. And then right here, I obviously didn't trust my work, so I should be actually running each of these cells as I go by and explain them. Otherwise, when I get to the important part, it will break. Okay, so now let's just print the values that we've computed so far. So we've computed a celerity of 8.8 meters per second, which is pretty quick, actually. That must be the celerity squared. No, it's already square rooted. That's bizarre. That seems like a big number to me. And that's practically falling through space. Our delta x is 1138 meters. And our initial computed best time step is 111 seconds. And so if we were to attempt to calculate an update at 120 seconds, that's too large of a time step. We have to use 111 seconds or smaller to guarantee stability. And in Sturm's book, he has an entire page that explains the purpose of that stability. As engineers, we have a choice. We could read the instructions, or we can just try it, and when the thing starts to go unstable, we'll redo it again with a smaller time step. And that works in a lot of practical engineering situations. It's probably not too advisable if you're trying to fly a spacecraft to Mars, and those corrections are fractions of a minute of angle that guarantee that you hit Mars or you end up in a spiral around Jupiter, which wouldn't be good if you're trying to get to Mars. I don't know why I'm thinking about Mars and Jupiter. I guess the software is Jupiter. And so there's our delta x and our delta t. And I have set a iteration max, which means it's going to attempt to do 5 time steps. And again, when you're doing either homebrew stuff or professional analysis, it's in your best interest to control the number of time steps until you are comfortable that you have set up the conceptualization of your problem into a stable fashion. In this case, this is a steady flow problem, so 600 may not be long enough to get to equilibrium, But what I'm looking for initially is that it appears to be tending towards an equilibrium solution rather than oscillating. You'll see what I mean when we get to the number part. And now some display functions, and there's no particular reason that they have to go here, except that it's convenient to have them. We have two of them. The first one simply writes to the console the contents of our depth and velocity vector, y and v, and it takes the time and the current time step, and it's just a little function that builds a table. And this is of more use to us just to supervise the progression of our solver. The other one is a plotting function, shamelessly stole from the internet, and I actually didn't even cite whatever blog I stole it from. I didn't steal it as is. I stole a smaller version of it, and then through the genius of trial and error and just plain stubbornness, was able to get it to plot two lines in the same plot. I literally have no idea what half this junk does. But I mean, I know that plt.plot generates a plot somehow. And I know that plt.title puts a title on that plot, X label, Y label, and then the show instruction renders it to the display. So again, that's all a good civil engineer needs to know. And now comes the hard work. All this, which I'm scrolling down quickly at first on purpose, that is the translation of those two update equations up above into computer mumbo jumbo. So we have a time counter, and we keep track of elapsed time because it wouldn't be very important to do this. And I have this instance where we print the start conditions. And let me, just for fun, split this cell out. Oh, good, it worked right. And we'll actually plot the start conditions. Let's see how to get the, we'll take, so let me go ahead and run those. So those are now loaded into the computation environment. We're going to set our time counter to 0 and our elapsed time counter to 0. We will print the start conditions. And so currently we don't have spatial locations associated with it, but position 0 is the left edge of this drawing, and position 10 is down here. So the depth is set to 8 everywhere, and our velocity computes as 1.38 everywhere. Our current time is 0 seconds. The best time step length that we expect to use is 111 seconds. And let's see if the plot will work. Let's see, is double X defined? It is. Bottom is. So what this should produce, unless I have screwed up monumentally, which happens, I should produce two parallel lines. One of them will be brown, one of them will be blue. The one that is blue should be a distance of 8 meters above the brown line. So it should be two parallel lines sloping from left to right. Let's see what happens. Oh, thank heavens. So there's our starting conditions. So we already know that 8 meters is too deep for that picture to be sustained because the normal depth in this particular channel is around 5 meters. So it can't sustain that, so that blue line has to change. And now we will go through the time stepping loop. I'm just going to slowly go through this, highlight the important parts to you first, and then we'll go ahead and run it. And I know it runs because I have something here. Now there's something going wrong at the boundary because I just barely got it running. And would be encouraged. I now need to go back and fix. I got something wrong with the downstream boundary condition. So we're going to start our time stepping. And so we're going to go from 0 to k max, where I time is just a counter, and it keeps track of how many times we have traversed this loop. The next thing I've taken is we're going to do something called adaptive time stepping. And what we're going to do is we're going to compute the smallest time step that we can use based on the worst case of any of the computational cells. So for that, we basically compute a Courant number in a cell. We compute the time step that would be associated with that Courant number. This is based on a formula taken right out of Sturm's book. And then we determine if our best time number is less than our current best. If it is, we change that to the current best and continue. And then when we're done, we have a time step that's now based on the largest possible time that we can use throughout the system. And the largest possible time we can use is the time indicated by the cell that has the smallest Courant number. So the biggest time we can use for the whole solution domain is based on the smallest time for any particular cell in the solution domain. I think I'm butchering that when I say it. But the part where things are moving the fastest requires a shorter time step, and that is the limiting time step for the entire solution domain. There are much more elaborate ways of doing it where you can actually try to solve things at different times. But that's beyond the scope of us doing a homegrown one. So now we have the time step to use. So now let's do those finite difference equations, those updates. We're going to do it for 1 delta t. So if you recall, when we developed it last time, we had this this constant r, which is to just replace r by 1/2 delta t over delta x. And that makes the coding a little simpler. So we have an upstream, we have our upstream boundary condition and our downstream boundary condition. What this section of script is doing is it's implementing a negative characteristic curve. If you read Sturm's book, where I pointed out the characteristic method last class meeting, there were 2 characteristic curves at any point. The upstream one, here we're using the negative curve to use the known upstream flow depth in this case to determine the required upstream velocity. And on the downstream end, we're going to use something called the positive characteristic curve, essentially do the same thing. We use the known downstream velocity to compute, the known downstream depth, the pool depth, to compute the required downstream velocity. So as boundary conditions go, these are the 2 easiest to manage. Because if we know depth and we know discharge, then velocity is pretty trivial to determine. Where it gets interesting is where that discharge term is changing with time. Like, for example, we're putting in a hydrograph at the upstream end, because then we don't know velocity explicitly, because the discharge affects the depth as well as velocity. So that's where these characteristic curves come in. I will probably in our next class meeting take some time to explain the use of the characteristics to map boundary conditions. The next part are the interior nodes. Those are just the equations as written. So we're going to start counting our cell center I from position 1 all the way out to the nth position. We compute our flow area from the cell to the left of the current cell, top width to the left of the current cell, wetted perimeter to the left of the current cell, the ratio of area, the hydraulic radius based to the left of the current cell, and a friction slope. So area, top width, perimeter, hydraulic radius, friction slope by Manning's equation. We do the same to the right of the current cell, area, top width, perimeter, hydraulic radius, friction slope. And then we use those to produce spatial averages, which are going to go into the update equation. Our geometric spatial averaging is shown here. Our friction slope spatial averaging is shown here as SFM. Our velocity spatial averaging and our depth spatial averaging. And now we have all the pieces we need to implement those two update equations. So the first thing we'll do is we'll update the velocity term. So essentially what that expression is that finite difference equation for velocity that was derived from the momentum balance. And it says use the spatial average velocity minus r times g times the difference in depths downstream minus upstream minus r times the spatial average velocity difference in velocity downstream minus upstream plus g times delta t times S0 minus S sub f. So it's literally the momentum equation for one computational cell. Then we compute the depth values in a similar fashion. So our projected depths are the spatial average of the current depths, and then the variation of velocity. So that's inflow minus outflow, and then the depth taper of the water surface. And that's done for one spatial location, and then we do it one at a time for the other ones. So when we get done with that, we've completed all of our interior loops. The boundary conditions are taken care of. They're semi-independent. They depend on whatever the current values are to run these characteristic curves. And now we increment our simulation time, increment our loop counter, take the projected values and put them back into the original spaces for velocity and depth. And then if it's time, we'll write some output. And then this is something I added is I'm going to artificially inflate the time step, and that's to force an adaptive update to occur. The adaptive time stepping, as it's implemented here, has a bad habit of kind of just losing interest and coming to a constant. So I artificially make it too big. And if it passes the artificial too big, then we're happy. So the time steps they will double in size every chance they're allowed to. And then finally, we will plot whatever it is at the end of our simulation. So I'll go ahead and run this. So here's what the output we should get, unless I've buggered something out. So we start at time 0, and that is not correct. Oh, I know, because I've actually restructured the code. We begin the time stepping. Okay, that is indeed time 0. I guess I do have to rerun it. All right, fingers crossed, everybody. Oh, thank it's okay to thank the gods of data when stuff doesn't explode in your face. So time zero, we had these two parallel lines. I don't know what happens if I try to plot every time step. I don't want to risk that. At 111 seconds later, which is one time step, we have our flow depth at the upstream end is dropped down to 5 like it's supposed to. And it made that change because of the required boundary condition that we imposed by the characteristic line. And that 5 should not change from now on. In doing that, we get a negative velocity at that point. We have to ask ourselves, does that make sense? And the answer is, yeah, I think so. So here was our starting condition, this upper red line. And we have forced that to come down there to 5. If the next one is still up here at 8, that is the shape of our water surface. And what does your intuition tell you? Which way is velocity going to go in this location? It's got to go that way.
Left.
So that's why you get the negative velocity value. That's actually a fairly incredible amount of acceleration from a positive 1.3 to a negative 1.2. But again, those are not necessarily realistic numbers at the beginning. And then at the end of that time step, it calculates our next time step length, which it thinks is going to excuse me, it returns the time step length we just used. And then we go to our next time, which is 214 seconds. And this velocity is still negative, but getting smaller. And now we see the depth at the next cell has dropped down. And so what we're seeing is a reverse wave propagating this way, and this is kind of slowly draining out to the right. And then we go to time 315. And notice our next projected time step length is 103 seconds, which is kind of good. It is getting smaller, which is, I think, to be expected during the transient phase. And now we have 5, 5, and 5. Everything else is 8. And these ones are starting to change. And at this point, that's what our water surface looks like. So let me pose the question. Does that look like equilibrium to you yet? I would say no. So we can now go back and we'll make some changes. So that was 10 minutes. Let's run it for 100 minutes. 6,000 seconds is 100 minutes. So a little bit more than an hour. And this is organized in blocks, which would not be how you would do it for a pay-for project. And it disobeyed me. That's better. And we've now, at this point, let's just look at the last two time slices, 5, 5.092, 7.68, 5, 5.092, 7.68. The velocities look pretty much the same. So we're pretty close to equilibrium after about an hour in this 12-kilometer long channel. So we've run a transient solver to equilibrium, which is kind of a so what, but let's see what happens when we do this same problem in swim. So at this point, let's go ahead and delude ourselves in thinking, okay, I've got a transient solver kind of sort of working. I'm still not comfortable with boundary conditions just yet, but it seems to work. Let's test it on some other tool. So I'm going to actually try to go to my Amazon Web Services instance for two reasons. One is Anna contacted me earlier and was having trouble getting to hers, and so let's see if I have the same trouble. In which case it's because it's in Ohio and AWS isn't working right now. If not, we'll go ahead and do a call tomorrow and figure out what's wrong with yours. So I've got to log in, sign into the console. My iPhone corrects everything I ever try to type. It makes up words I've never even heard of. This one, where money's involved, can't do it. Go figure. Okay, it's this guy. So this is what you were having happening, and it just hung up right here. Looks like it's going to be doing that for me too. That is really annoying when that happens. I'll try locally on my machine in a second. So if it's going to connect, it would be faster than this. So things I do to attempt to regain control. First thing, go ahead and issue a reboot. Let it do it. That usually happens pretty quick. I'll try one more time. Okay, that's not going to work. So here's the slightly more violent way. We go ahead and stop the instance and then restart it. That's what you and I as human beings really think rebooting is. It takes sometimes 5 or 6 minutes. So I issue the stop command, and it's doing its stopping thing. So when the start button becomes available again, it will restart. Now the only unfortunate thing that we're doing is we are giving up. Oh, I had no remaining burst capacity anyway. You get about 140 minutes a day of clock time, and what happens when you do a restart is you're basically giving up a day's worth of computation time. They restart you at about 30 minutes or something. So it's enough to regain control of whatever you're doing. I am loath to do it on the content server for the classes because it's supporting a bunch of different classes I teach. And I really detest doing a stopping and starting because most of the time it just works good and I accumulate like 2 days worth of computer time. And if you do a stop and start, you basically lose your accumulated time. It's like keeping money in the bank. You know, it's your money until you actually need it, and then they take it away from you. It's a slight form of evilness on Amazon's part. But to their credit, their services cost about 1/10 of what other vendors offer it for. So they pretty much put it on you to be sure, or to do your best to get your stuff all locked down and working correctly. But since we're just experimenting with it and learning it so we can put it on resumes and say, yeah, I know how to do Amazon Web Services, that should be worth a job. And you will be able to say that. You can honestly say that. Let's say, go, you're an expert at it. No, I didn't say that. I said I've used it. So we'll let it try to come back up in a second. It's usually pretty quick about it. So stopping and starting is really rebooting. Clicking the reboot button just sends an interrupt signal, and if it's going to work, it works. It works the first try. There we go. Okay, so here goes nothing. If this and given that I have Anaconda running on it, I may have had an open process running, so that should disconnect the process. These are dirty little secrets of cloud computing that they never tell you when they first get your credit card number. When you go work for a company and they're using if you work for a company that has its own data center, the same kind of crap happens, but at least you can pick up a phone and yell at somebody. Okay, so I should be able to connect. Come on, give me my connection. There we go. So that's how you regain control of your cloud computer. The only meaningful advice I can give you is when you exit your cloud computer, try to remember to turn everything off. Isn't the right word, but try to disconnect all the services that are running on it. So close all the windows, close all the tabs, stuff like that. Why did the computer shut down unexpectedly? So now we'll go ahead and don't worry, some operator is going to read that and it'll make his night or her night. Notice I said the computer was a POS, not the people working in Amazon. Although probably that's true for some of them. I don't want to turn my power off. I want to bring up my swim model. Hello. Oh, that's what I get for telling them it's a POS. Let me wait for the connections to. I'm getting a lot of network lag, so I'm running this out of their Ohio server farm, so there's no telling what the electricity or weather's like in Ohio. Anybody know? I think it's as cold there as it is here, although they're used to cold weather up there.
It's pretty much like the entire middle of the US is like below freezing.
Yeah, so they're probably throttling everything to be able to provide any level of service. Okay, so here is our swim model, and we will try to model the same situation. So let's go ahead and we're going to need to get some inputs from swim, for swim. Okay, so to get it into SI units, we'll go into, let's see, Miller genuine draft, nope, cubic meters per second. And we have 10 reaches. Actually, let me start from the downstream end. So there's our downstream one. So that's position 0. That's position 10 in our model. So 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I just drew those there. Their relationship to each other is just graphical. It's not that they're different distances apart. The next thing I'm going to do is I will create my conduits, but let me go ahead and make my life a little bit easier. I'll go to the defaults. And I don't want circles. I want squares. No, I'll go with squares. Our bottom width, as you recall, was 5 units. Let's let them go as tall as 10 units to be sure that they will contain our computed water. And our conduit length was 1138. Rectangular open, 1138. Our conduit roughness was 0.02. And our routing method is going to be dynamical wave. We don't care about the rest. Press the okie dokie button. Now we're ready to so now I'm doing the hard part of modern modeling, is drawing pictures. And all those years of playing in the video arcade as a relatively young person have finally paid off. Okay, killed me some asteroids here. Okay. So now we've almost set up the geometry. The next thing we have to do is, there's a reason I actually had that. We're going to need that to get the elevations. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nailed it. So I'm going to set the elevation of this guy to 12. I'm basically going to enter these numbers. And the last one's going to be at 0. So invert elevation, 12. .862. That's my best Slim Pickens imitation from Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. 9 point. He's passed away, but he would appreciate a college instructor in a backwater Lubbock teaching hydraulics to invoke his character from the movie. 8.586. Seven point. And there are interfaces, I'm not familiar with them in the EPA delivered interface, where you actually can pull up an entire table, and this data entry is a whole lot faster than going one object at a time. But I am possessed with having no idea how to do that. So actually not no idea, but I don't have it conveniently brought up. 4.034. 2.895. The recorder's still on. It always worries me when I'm doing this that I've forgotten to turn on the video recording. But looking at you all, it looks like I missed one. You seem comfortable, and yeah, I'm comfortable with the videos recording of 0.034. All right, if you say so. 0. Okay, our outfall depth at the downstream end is fixed. And if you recall, it is at a value of 8. The upstream end, we have an inflow of yes. And we'll let the computer program calculate the depths. Actually, we can do an initial depths too. I'll show you something cool. You can use the group hug feature. So we'll start everything at 8, just like we did our simulation, with the exception of this one started at 5. Okay, let's take a look at what we've built. So it looks like a rectangular slope channel, and more or less the same as we've built. If you recall, ours is the same. Literally, it looks the same. So this is at a little bit below 12, and up here above 20. And in this one, we recall we explicitly set them at 10 meters higher, so 12 to 22. Okay. Next thing we do is see a set inflow. Manning's end downstream boundary condition. I think this is actually ready to simulate. Let's bring up the general. For a great new rate you can get on time line, go to the general and save some time. So we have set up dynamic wave and flow routing. This is set to run for a 6-hour simulation period. And here's what I was talking about, time steps. So we can set our routing time steps. The default is 30. If you recall, in our simulation, we were all around 111. Let's try, how about 130? It'll automatically fix it. And then the reporting step is how often we want it to produce output. So our example, not that we're going to look at it, we were producing output about every 100 seconds, so every 2 minutes. So we can run this down to every 2 minutes, which would be 120 seconds. This is going to come at a price. The simulation will take a noticeable amount of time to run. Well, those are in hours. Hours, minutes, seconds. So we pretty much have everything set up as close to our homegrown simulation as we can get. And in a dynamic wave, in ours, we kept our inertial terms. The rest of this can be, I'm making a few changes, mostly just for fun. And then this has a automated time stepping routine. In our case, we were using a factor of 2. So that'd be equivalent to this being set at 50. And I believe we are okay and ready to go give it a try. So unless I have screwed something else up in the input, looks like I have. reporting time step or duration is less than the routing time step. Okay, so we will change that. Okay, so this is the result of the swim simulation after 2 minutes of simulation time. So that'd be 120. So that's somewhere similar to ours. So 5 at one end. We don't have plots, but they should be mostly parallel lines, and it is. So we will go on our swim one and we will advance 1 time step. And now we would be somewhere close to this. So we have a 5, 5.4 parallel lines, and then maybe a slight increase at the downstream end. So we got 5, 5.4 parallel lines, and then a slight increase somewhere at the downstream end. Let's go about 20 minutes, which would be 20 times 6, 1200 seconds. So the swim one now is somewhere similar to that, to this one. 5 at one end, and in terms of depth, it's steadily increasing, but you'll notice near the end, it's actually slightly higher than the end point. So you got this hump right here. So it's more apparent in the swim model. And if I was to critique the two on which one is likely to be more correct, it would be the swim model would be my choice. Let's go out to about 3,000 seconds, which should be 3,600 seconds should be like 30 minutes. I'm losing my ability to do arithmetic in my head. So here's our simulation. Here's the swim one. And we'll go all the way down to the end now because I think I've made my point. We were at our last outputs at 5,700 seconds, which is equal to 5,700 divided by 60 equals 95 minutes. So we get as close to 95 as we can without going over. 95 is an hour and 30 minutes. Yeah. Okay, so that's 90 minutes. 92, 94. That's about as close as we can get the two models. And at least visually speaking, we can argue that we indeed have the same answers. And so what we just did in swim is exactly what we did in our homegrown, our homebrew program. I was going to say the ones we rolled our own, but I guess we're not supposed to make references like that. Let's go take a look at the actual computed depths, because what we've printed here is not water surface elevation, but flow depth. And I think we can actually get flow depths from the swim model. See, by variable, by object. I want snow depth. Nodes. Depth. Okay, that's what I want. And I want to go nodes. Another good warning for you, Anna, is when we're doing it in I'm just going to take a couple of nodes. I'll take the top one, the middle one, and close to the end. In the cloud thing, it crashes pretty dramatically from time to time. So stuff that should work, you'll move something, it'll lock up and just go away. Good chance to work on profanity when that happens. Try to save stuff a lot. So what do we call this one? This is example 1. All right, node 11 in swim is our upstream-most node, and node 2 in swim is our downstream-most node. So node 11 should correspond to somewhere up here, our 0, and node 2 would correspond to this 10, just the 10, not the whole thing. So let's see what we get go late in time. So upstream end, we have a 5. We have a 5. Somewhere in the middle, we have 5 1/4, and our homegrown one is actually substantially different. Our homegrown one is more at 5.88, and then our downstream end, they're at 6.72, and we're at 7.6. Let me actually just add one thing to it. See what's actually happening at the outfall. That's the outfall I know is 8. That's going to be, that has to be perfect. Downstream. Let's go the one immediately upstream of it. And we know the upstream end is fine. That's 1, 2. Okay, so that is position 10, 9, 8, 7, 6, 5. Okay, so our position 9 in our model in swim has a value of 7.38 compared to our 7.6. Position 8 in our model, sure I got that right, outfall 1, junction 2. Position 8 in our model is 7.048, and in theirs it's 6.72. And position 5 in our model is 5.88 compared to swim's 5.25. So they're close. In some sense, there's no expectation they would be exact. I would like it to be closer than that. They're implementing different ways of computing the same process. Swim doesn't use lax diffusion. It uses a somewhat more sophisticated differencing scheme. At the risk of really embarrassing myself, and then we'll be done. Let's, for grins, just take a look at velocity. So we have velocities ranging somewhere between 2 and 1.3. We'll do our downstream most one, a middle one, upstream most one. So our downstream most one in swim is 1.57. We have 1.38. Somewhere in the middle, swim is 2.13. We're at 1.98, 2.03. And upstream most, we're at 2.11. They're at 2.21. So again, close. And close enough that we would comfortably say that our homemade model is representative of the kind of computations that must be going on inside of the professional model. Okay, you all look beat to death with that, so good, I have succeeded. Part of what you're paying for is good night's sleep, and I may have just contributed to that by boring you to sleep. And we will pick this up on Monday and continue. What we'll do on Monday is we're now going to take our homebrewed code, make some modifications to generalize it, and we'll actually try it with a real transient problem. And then we'll compare that to swim with the same real transient problem. When we get to true transient problems, the agreement here is quite a bit better than it will be when we do a true transient problem. But again, the same general behavior will be reflected in our homemade one, in our swim one. And at the conclusion of that, you can legitimately say that yeah, you know what goes on under the hood in swim. You know what's going on under the hood in Hydrograph. You don't want to go messing with it. I mean, unless you're really into that, because there's a lot of letters of the alphabet getting slammed around back and forth. All right, well, I will call that a night, and I want to thank you all for your attention. You've been good sports. I'm glad I was able to get my swim model running. And I hope that answered your question on why it wasn't working. Again, email me tomorrow if you still can't connect. We'll do a Zoom call, and I'll let you share your screen and see if I can help identify what's going on.
Yeah, I'll definitely give that a try. Thank you.
And I'm going to save my work, exit my swim, choose yes. Well, this is cool when it actually works. In fact, I never have to make Windows work on a Macintosh again. It's just worth the price of admission. And this is what I mean by shutting things down. I think you want to, so you notice I closed the swim, I closed all the open stuff. And I think what I want to do is go to the power switch and choose disconnect. And what that does is it should leave your virtual server still running, but it's not doing anything, it's idling. And then this message is normal. When you disconnect, rather than trap the disconnect, they just go ahead and declare it's a mistake. Please wait. So that's it for today. Thank you all very much, and I will see you on Monday. You've seen the homework assignments. At this point, technically, you've been exposed to most of what you need to know to be able to do them. On Monday, I'm going to talk more on how those boundary condition characteristics are managed, because all I did today was just show it to you. So have a great weekend. Stay warm for those of you that are in a cold climate. Stay cool for those of you that are in a warm climate, and have a great weekend. Be safe. Bye-bye.
Bye. Thank you, Dr. Cleveland.
Thank you, Dr. Cleveland.
Bye-bye.